Let's talk about conformational analysis. We'll start this lecture talking about Newman projections. First, we're going to understand what we mean when we use the term conformational analysis. We'll talk about analyzing ethane and propane, different conformations of those, and then we'll move on to a slightly more complicated example of butane. So we have lots of different ways that we've already talked about in terms of depicting molecules. If we look at ethane, right, we have a carbon here, we have a carbon here. The wedge bond means the hydrogen is coming out of the page. The dash bond means the hydrogen is going back. Same thing on this side. If we took the molecule and flipped it around, we'd get this kind of a view, right, where the hydrogen is in between these two hydrogens, and this hydrogen is in between these two, this one is in between these two, and this one is in between these two. This is called the sawhorse depiction, which is pretty much never used. What's much more common is something called the Newman projection, where the front carbon is depicted as such and the back carbon is a circle with these hydrogens on it. So imagine, if you will, that you're closing one eye and you're looking down this bond. These guys are going to be in the front and these ones would be in the back. That's called a Newman projection. So like I said, when you're drawing a Newman projection, the easiest way to do this, I think, is to start off with the front carbon, which is going to be like an upside down Y. In this case, for ethane, we have 3 hydrogens attached to that front carbon. So the front carbon is going to be the point right here. We don't draw a C there. In the back, we have a circle. So this is the back carbon, and we have 3 hydrogens attached to that back carbon that we're going to draw in like this. So you want to get familiar with how to do this for any molecule, not just ethane. So for example, let's say we had this compound, which is called actually 2,3-dibromobutane. What we've left out here is that there's a dashed bond to hydrogen that's going back here, and a dashed bond to hydrogen that's going back here. So if you're an eyeball and you're looking down this bond, what you want to do at first, like I mentioned, is draw the first carbon. So if we're going to do that, it's going to be an upside down Y. If I'm looking down this bond, the bromine is going to be on my right hand side at the top, and the hydrogen is going to be on my left hand side at the top, and a methyl group, a CH3, is going to be pointed down right here, CH3. So this carbon right here is going to be this one right here. The back carbon is this one, which we're going to draw as a circle. Coming up is a methyl. So this here is a CH3, right? Bonded to this carbon. On the right-hand side is a bromine. On the left-hand side is a hydrogen. So the reason that we want to learn how to draw Newman projections is because these molecules are constantly rotating. The bonds are rotating, and we want a way to depict that on paper. So you can imagine in ethane, this carbon can rotate around and this back carbon can rotate around. We have infinitely many different conformations or ways that these atoms can be arranged as that bond rotates around. The two extremes we're going to call staggered. The lowest energy conformation is going to be staggered because each one of these hydrogens has a cloud of 1 electron surrounding it, and those electrons are negatively charged and they repel each other. So this staggers those electrons as far apart from one another as possible. So this staggered conformation is always going to be the lowest in energy. What's more difficult to draw is when those two electron clouds start to eclipse one another. That eclipsing conformation, as those electron clouds are getting as close to one another as possible, that's going to be the highest energy conformation. So as this front carbon rotates around, we're going to go from low energy to high energy, and I'll show you a graph of this in a second. The important point here is that single bonds can rotate, and they will rotate. And so we want to be able to depict all those different conformations or ways that those atoms can be arranged with respect to one another. So if we graph this thing, what do we get? Well, first we start with our lowest energy staggered conformation right here. This is called energy well because we're at the lowest point of energy. But for example, let's imagine that this hydrogen starts to rotate towards this hydrogen. This hydrogen starts to rotate towards this hydrogen, so we're rotating the front carbon. As these two hydrogens get closer to one another, and as these two hydrogens get closer to one another, we start going up in energy. And that's what so this scale right here is potential energy, and this is degrees that we rotate. So as we start rotating, we're going up, 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 up in energy till we get to our eclipsed conformation. We started staggered. At the low energy point, we went up to the high energy. But then this hydrogen is going to keep rotating around, and we're going to get back to a staggered conformation. Then it's going to keep rotating around, and we get to an eclipsed conformation. Then it keeps rotating around, staggered, eclipsed, staggered. Notice that the difference in energy between the lowest energy and the highest energy, 12 kilojoules per mole difference between these two conformations. So, but actually there's plenty more energy than that available at room temperature, so ethane is constantly spinning around really, really fast, going through both these eclipsed and staggered conformations all the time at room temperature. Okay, let's look at propane. Remember, propane is 3 carbons, 1, 2, 3. We have a CH3 here, and let's say we look down this bond. We have a hydrogen coming out and a hydrogen going back. We have 3 hydrogens here. Okay, so on the front carbon, we have a methyl and a hydrogen and a hydrogen. So we draw front carbon as an upside down Y. We have CH3 and an H and an H, and in the back, and our lowest energy conformation, we have our 3 hydrogens, right? So this is going to be our lowest energy staggered conformation. As we go up, we start to eclipse till we get to our eclipsed, fully eclipsed conformation, where the methyl group is now eclipsing a hydrogen. Notice that methyl group is bigger. The electron cloud around methyl is bigger than it is around a hydrogen. So in the previous example, we had 2 hydrogens eclipsing. Now we have a bigger methyl group eclipsing that hydrogen. So notice that the difference in energies is now 14 kilojoules per mole instead of 12, but notice we still have the lowest energy. We're just alternating between staggered and eclipsed, staggered, eclipsed, staggered, eclipsed, staggered, etc. Things get much more interesting and or complicated when we get to butane. So if we think about butane, and we want to think about the conformation about the middle bond, we have 4 carbons, and we have a CH3 and a hydrogen and a hydrogen, 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 CH3. So if I'm an eyeball, let's see here, I'm looking down this bond, coming up is going to be a big CH3, and to the left and right are going to be my 2 hydrogens. In the back we have 2 hydrogens and a methyl. So what you want to think about is that these methyl groups are much bigger clouds of electrons. So the most stable conformation, we're going to call this the anti-conformation, because the biggest groups are the farthest apart as possible. But as we rotate around, so as this thing starts rotating towards the methyl in the back, notice that these clouds of electrons are getting closer to one another. So we have 2 different staggered conformations, right? We have the anti-staggered conformation, but now we can also have a second staggered conformation, which is different in energy, called a gauche conformation. We're still staggered, but now these methyl groups are closer to one another, so that's going to be a higher energy staggered conformation. Let me show you what I'm talking about. So notice how this potential energy diagram looks very different, or somewhat different than the one we just looked at. So the lowest energy conformation that we said is the anti-staggered conformation. As this methyl group comes around, we stagger a methyl and a hydrogen and a methyl and a hydrogen. There's 16 kilojoules per mole associated with that. As this methyl continues to rotate around, now notice what happens. We get a gauche. But notice that there's about 4 kilojoules difference between anti and gauche. So these are both staggered conformations. One is slightly higher in energy. This is different than the previous example, right? This is not the same energy as this. This is a little bit higher. As we continue to rotate that methyl around, we get to the highest energy conformation where two huge methyl groups are both eclipsing one another. So that's going to be the peak. And notice, actually, there's a difference in energy between these two peaks as well. This one is higher energy than this one. So there's two different energy staggered conformations, and there's also two different energy eclipsed conformations. So this would be the highest in energy. Then we go back down to the gauche. Then we go back to our lower energy staggered conformation, eclipsed conformation. Then we go back again to our anti. So we can just keep rotating around here. What's important to notice is that the eclipsed conformations are always going to be higher in energy than our staggered, but we can have different energy eclipsed or different energy staggered conformations. As I mentioned, what you want to notice is that the wells, the low points, the energy low points are always going to be staggered conformations, and the peaks are always going to be eclipsed conformations. This one would be the eclipsed conformation where both methyls are eclipsing one another. Two big groups eclipsing each other is going to be the highest energy interaction that we're going to look at. So what's important here? Well, we just talked about Newman projections. You want to be able to look at any molecule and be able to draw a Newman projection and analyze the relative energies of the different Newman projections. How do we do that? Well, you want to think about when you're drawing a Newman projection, you're looking down a carbon-carbon bond. What's in the front, what's in the back, be able to figure that out. Then, more importantly, what you want to do is be able to use Newman projections as a tool to evaluate the relative stability of different conformations, remembering that eclipsed conformations are always going to be higher in energy than staggered, and that if possible, always keep it's going to be lower in energy to keep larger groups away from one another.